Okay, so my mobile phone said we can officially start the second lecture. And this lecture still will be relatively simple and mostly about really very basic things. It's important because in astronomy, you usually deal with two types of phenomena. One type is when you understand the phenomenon, but you want to get as precise measurements as possible, with 1% accuracy, for example. And then you have to be very careful how you compute. You have to include all effects, the best knowledge you have. On the other hand, there are phenomena where you just notice something on the sky or in the computer or whatever, and then you have to estimate what this is rather fast, because otherwise you would spend much time on a concept which is just not working. So we will talk mostly today about those key parameters which are characteristic for accretion process and which allow to estimate things fast. So to give you additional motivation, I posed the following problem. We observe a globular cluster in X-rays, and we have optical observations of this cluster. We know the distance to the cluster, because if we see something in the optical band, usually we know the distance. There are many ways to measure the distance. Then we measure X-ray flux from a source. And from the measured flux, we can calculate X-ray luminosity, for example, 5 times 10 to 37 in ergs per second. And then we consider what it could be. It may be difficult, but if we measure the radiation spectrum, for example, the temperature the emission looks like black body, and the temperature is of order of 1.5 keV. What this can be? A white dwarf, for example. So, or maybe intermediate mass black hole. So in order to answer such questions immediately, you have to consider a number of important parameters. And the first important parameter is the Eddington luminosity, and then Eddington ratio, which is the ratio of the luminosity of the source to the Eddington luminosity. So the Eddington luminosity is defined in such a way that we have a spherical body, whatever it is, this body, and the body is accreting, the energy is dissipated, so then there is a lot of radiation also coming out from this body. And the obvious question is, can this accretion be arbitrarily high? The answer is no. And to see how it works, we have to consider the electron. And we do the following assumption, that the material here around is fully ionized. So what we have to consider is actually this free electron, not bound electron. And we have to consider what this electron will do under the force of radiation pressure. So if the luminosity of the body is F and the radius of the body is R, then the radiation flux is given by this expression. That's quite clear. So now we have to calculate the radiation pressure to see whether this radiation pressure will prevent further accretion or not. In order to do that, we have to know something about photons. So in principle, you know all that, but I think it's always useful to remind some things about a photon. So in general, not just for a photon, the relation between the energy and the momentum in special relativity is given by this formula, where E square is equal momentum square times the light speed square times the rest mass plus rest mass square. So if we consider the Newtonian situation, we assume that this is small in respect to this, and we will get some constant value because this will still remain, plus half mv square, which is the standard expression for kinetic energy. On the other hand, for photon, the situation is the opposite. Photon has mass equals 0. So we have immediately the relation between the energy and momentum for photon, which is E equal momentum times the light speed. Now we need an expression for the energy. And in this case, we need quantum theory, because you probably remember that the energy of the photon is equal Planck constant times the frequency. This is what I was explaining. Słucham? Ale to porozmawiamy, to nie jest ten telefon, na który ja czekam, ja teraz mówię wykład. Proszę zadzwonić, albo ja odzwonię za 1,5 godziny. It's not that one. I was waiting for. Sorry for that. Okay, where we were. So here, because you notice that Planck constant is here, then the relation is by definition of quantum nature, and Planck constant was introduced by Planck in 1901 to solve the problem of the black body radiation. We'll slightly talk about it later when we later talk about emission. The same conclusion that energy is emitted in the form of quanta was reached by Albert Einstein, and that was even more intuitive because he was able to explain the photoelectric effect. So he noticed that really a photon is not just a wave, but it's a particle, and its energy of a single photon is proportional to the photon frequency times this Planck constant. So sometimes we use frequency, sometimes we use wavelength if it is more convenient, depends on the situation, but we have, of course, the relation between the wavelength and the frequency, which has this form where c is the light speed. So now, if we defined on the previous slide the flux F, right, which was the luminosity divided by the surface area of the body. And now this flux is energy per second per unit surface, like centimeter square. In this case, we do not care about the radiation wavelength or frequency. So we can say that the force of radiation, which we look for, is given by the gain of momentum. So if electron scatters or absorbs photons, the electron gains momentum. So because we have this relation between the momentum and energy, to get the momentum, we have to divide the energy by the light speed. So we have to divide the flux by the light speed. So this will be the momentum rate per unit surface. So now we have to know the surface of the electron, or the cross section, saying more scientifically. And in the case of fully ionized material, this Thomson cross section usually described as sigma t is equal by this formula. And notice that here in this formula, there is no Planck constant. So this formula is purely classic. That's kind of amazing, but this is how it works. So next digression. This Thomson cross-section is actually connected to the classical radius of the electron. It is a concept which is practical because it helps to intuitively understand what is happening. On the other hand, in principle, you should be using quantum electrodynamics to describe everything. So this classical formula is a significant simplification. But nevertheless, it's nice to understand how it is working. So here you see that you have the radius, and you got the radius using mc square and e square. So if you think what mc square is, this is the rest energy of the electron, rest mass of the electron times e square. Then if you use e square and the radius, you can also construct another energy, which would be potential energy of the interaction of electron with itself. So you immediately, even from the dimensional analysis, you can see that if you put the request that the rest energy of the electron is equal to the potential energy of the self-interaction of electron, you will get the classical radius. There is, even you can find it in Wikipedia, there is more advanced derivation of this expression for the classical radius. You imagine that you have a sphere with the total charge E, like for electron, and you try to compress it going from infinity and making this more and more and compact, and you calculate the energy of the sphere, and finally it gets equal to mc square, and you already know that you have a kind of a problem. You should stop there, and this is this classical radius of the electron. Compression, perhaps it's not the right picture, because the electron actually need interaction, other interactions behaves like almost point-like particle. So perhaps the better intuition is that electron emits virtual other electrons, and they are quite dense close to this, the original electron. And then this kind of virtual particles present around, this would be consistent with quantum understanding of the process. This forms kind of a wall. So if the photon passes at larger distance, the photon does not notice the electron, but if photon passes here, it just hits this wall and gets scattered. And that intuitively also explains why the cross-section does not depend on the wavelength of the photon. So it's a very nice picture, although brute force and not full quantum electrodynamics, but I'm not going to give you a course of quantum electrodynamics because that would take the rest of my lecture. So in numbers, this so from this kind of derivation, you have some problem of error by 50%, but it's not a big problem. As for the value, this classical radius of electron is 10 to minus 15 meters or 10 to minus 13 centimeters. And this expression for this classical radius appears in many places. For this Thomson cross-section, we will be using that quite a lot. Later, I will also mention the relativistic version, namely Klein-Nishina cross-section. If you do quantum theory, this is also the length scale where you should do the renormalization or gauge theory, etc. So, of course, this intuitive picture is oversimplified. You shouldn't believe that this is really a sphere like that. And this classical derivation is not precise. If you follow it, you will notice that you have an error by 50%. But it's not a catastrophe, right? For order of magnitude estimates, this is really quite useful. Anyway, so we continue with this. We have this Thomson cross-section. So if we know that this is the momentum gain per unit surface, we multiply by the Thomson cross-section. So in order for the accretion to proceed, this force due to radiation should be smaller than the gravitational attraction of the infalling material. Otherwise, if this is larger, then radiation pressure will puff everything and it will stop the spherical accretion. Notice here one thing. Here, mass of the proton appears, not mass of the electron. And this is because the plasma in general should be neutral. So if you try to push away electron, one proton will follow. So you have to push actually the proton. In that case, you can neglect the mass of the electron, which is almost 2,000 times smaller, so forget. So assuming the limiting value and then putting here the luminosity, you see that the radius will cancel and you will get the limiting value for the luminosity, which is equal 4 pi g m. M is the mass of the central body, proton mass, light speed, and Thomson cross-section. And in numbers, this is something like that, where this is the mass and this is the solar mass. So here we express the mass in solar body units. So of course our sun is not radiating with super Eddington luminosity, because in those units the solar luminosity is 10 to 33. So we are 33, 5. What is 38 minus 33? Whatever. Many orders of magnitude below the Eddington ratio. So notice that there is no dependence on the radius, by the way. And also this is strictly valid under assumptions of spherical geometry, fully ionized material. And small note, you can check, well, this will be actually a homework. You can check that you personally shine with luminosity quite close to Eddington luminosity. So maybe some of you should start to worry. Now the second quantity, which is important, is the radius, but we already discussed in the case of accretion efficiency that the nice way to measure the radius is through the ratio of the radius to the Schwarzschild radius, and this is how it looks in numbers. Sometimes I have meters, sometimes I have centimeters. Sorry.
I have a question.
Yes.
Why don't we consider the interactions between the photons and the protons?
You mean in the previous case?
Yes.
Well, we because the force acting from photons on protons is small. But for that, you need quantum electrodynamics to make sure. So the interaction with electron is larger. Actually, this electron radius is pretty large. That's how it happens. Another interesting thing, which is important in the case we observe variability, and as you may know, all accreting sources are actually strongly variable. So this minimum time scale is quite important. And we can draw some immediate conclusions from that. So the minimum time scale can be estimated in such way that if you have changes in emitting body, then different parts of the body should communicate at least through photons, right? So then this minimum time scale should be the radius divided by the light speed. And then we can express it using the ratio of the solar mass to the mass to the solar mass and the radius to the Schwarzschild radius. So, for example, if we consider black holes, then this radius is of order of 1. But it depends on the mass of the black hole. So if we consider neutron stars or solar mass black holes, something like that, then this time scale is really a small fraction of a second. It's milliseconds, microseconds, something like that for galactic sources. On the other hand, for a supermassive black hole, let's say 10 to the 8 solar masses, this will be 10 to 3 seconds. So the processes, from our point of view, all processes in AGN are much slower. Sometimes it's really very, very convenient from observational point of view. For example, probably you saw this image, right? Everybody saw this image, because it was even in newspapers. This is the first image of a black hole. Now, in the title, it's an image of a shadow. This is not quite proper use of this word shadow. This is the silhouette rather than shadow, but does not matter. So the first source which was measured was M87, and that is it for the moment. Why? Event Horizon Telescope observed both M87 and Sagittarius A star, the Milky Way black hole. The angular size of the two are almost identical. There is factor 2 difference, and honestly, I'm not sure at this moment which one is somewhat larger. I think Sagittarius A star is somewhat larger. But the problem is that the project for Sagittarius A star failed so far. They were able to see only just the bright cloud without this black spot which marks the photon orbit. And probably what happened is the difference in time scales. Here, the integration of the image has to last a couple of hours. And the mass in M87 is much larger. This mass is more than 10 to 9 solar masses. So this time scale, if you put this value to this, is long. So if you do the snapshot, it is a snapshot. On the other hand, the black hole mass in Sagittarius A star is 1,000 times smaller. It's minutes. So if you have any episodes of bursting or whatever, and then you do the exposure of several hours, you get a mess, you average. And this is probably the reason of failure of this project for Sagittarius A star. And they cannot do shorter exposure because then they would not collect enough photons. So the time scale, as you see, is important. So if you choose a source for observation, you have to check those things, right, to optimize for the project. Of course, in the case of galactic sources, nobody even tries to do this kind of thing because it's not just the exposure time, which would be microseconds, but it's also the additional problem, angular resolution, right? We will never have it. Okay, next one is accretion efficiency. We talked about it already, and I just stressed that this does not depend on mass, but does depend on radius. Eddington accretion rate. Since we defined already Eddington luminosity, then introducing Eddington accretion rate is relatively simple, but you have to pay attention to what you see in published papers. The problem is the following. The luminosity, physical luminosity, is defined by m dot accretion rate times c squared times the efficiency of accretion. And this luminosity, if it is equal to the Eddington luminosity, we get the Eddington accretion rate. As simple as that. This is when expressed in numbers, but there is this efficiency. And the efficiency, as we discussed, is different in different processes for different objects. So you have to say something when you give the Eddington accretion rate or the accretion rate in Eddington units. This concept is used mostly in AGN, and then most of the people assume that the efficiency is 10%. This is what I do usually. Although in reality, this efficiency will depend on the mode of accretion, and it will depend on the spin of the black hole. But other people, to avoid the problem of efficiency, they assume efficiency equal 1. And that is totally misleading because they say, oh, we have super Eddington ratio, Eddington accretion rate equals 3. But if they use the efficiency 1, which is not really realistic, 10% is much better, then it's actually not super Eddington. So every time you see the accretion rate expressed in Eddington units, check the units. This is important. There is no such danger for luminosity, right? Because then efficiency does not enter the definition. Okay, now we will be a bit closer to the spectra because, you know, the spectra of objects in astronomy, they carry a lot of information. So the simplest thing to determine is the maximum energy which you expect from the accretion process. And the simplest case to discuss is like we did for efficiency. We assume spherical accretion. We assume that the body has a surface and the single particle hits the surface, dissipates the energy, and then all this energy is converted into a single photon. So that this energy is given by this value. Well, I calculated it for a proton, actually. So if this is expressed in MeV, then this maximum energy is something like 500 MeV. 1 GeV. This is quite a lot. We can also express that if those particles are thermalized, which is not obvious, but it can happen. It does not always happen. Then this temperature would be above 10 to 12 kelvins. Immediate note, this is not what we usually observe. In observations, we see quite frequently spectra from thermal plasma, but then the corresponding temperature is rather 10 to 9 kelvins and not 10 to 12. And this is because we observe emission from electrons. And here we calculated the energy from protons. And if the flow of energy from protons to electrons is not very efficient, or the cooling of the electrons is efficient, and this is always efficient, then this temperature will be lower. But anyway, this is the maximum temperature for ions, and from time to time, this will be quite useful. But this is, of course, in the case of optically thin accretion process, spherical, optically thin. That's the most important assumption. And this gives us this maximum energy or maximum temperature. On the other hand, we can also determine the minimum temperature. And to get the minimum temperature, we have to assume that accretion is optically thick. So the material is really dense, thermalized, accumulates, let's say, at the surface of the emitting body. And in this case, the radiation is always, for a given flux, the radiation is most efficient, the temperature is the lowest if the emission is locally black body. This is always true. Any departure from the black body under the same flux rises the temperature. So to get the temperature, we need to assume black body radiation. So if we have a body of the radius r and luminosity L, we can determine this black body temperature. And we can express it again in dimensionless units. I mean, here it is dimensional, but using the ratio of the luminosity to the Eddington luminosity, radius to the Schwarzschild radius, and mass to the black hole mass to or mass to the solar mass. So if we see that if the accretion is really Eddington and the radius is of order of Schwarzschild radius, for example, for a neutron star, this would be very nice approximation. The temperature you get is of order of 10 to 7 kelvins or 4 keV, order of magnitude. Very good estimate, real value is 2 times smaller. On the other hand, if we think about AGN, of course, we don't have a surface, but you will see that the scaling is not that bad, even in the case of a black hole. But the problem appears that here you have the ratio of the mass to the solar mass in the power 1/3, 1/4, right? So if you have mass 10 to 8, then this factor will give you factor 100 in the numerator is on the top, right? The denominator is in the bottom. Okay, so factor 100 in the denominator. So then the black body temperature will drop from 10 to 7 or emission in X-rays to 10 to 5 to emission in UV. And this is immediately informing you also about the difference in accretion disks in AGN and galactic sources. There is 2 orders of magnitude difference in temperature, and you should observe AGN in UV, far UV, and you should observe galactic accretion disks in X-rays. So now if you think about this problem of this unknown X-ray source in a globular cluster, which I defined before, then you can check for yourself that this 10 to 37 luminosity would be too high for a black hole, white dwarf. So it should be likely neutron star or a black hole. Also not supermassive black hole, because then the temperature will be too low. So you see, simple estimates are really useful for selection objects. Now the next value, magnetic field. I will not use that much the magnetic field in my lecture, but there will be a lecture on magnetic field and jets and so on. So this is also important. And to get the order of magnitude, you can use the energy density. Just the rough idea, right? So the energy density can be of the magnetic field is equal B squared over 8 pi. And you can compare it with radiation density, for example. So you can assume it's kind of equipartition. You can also assume it's equipartition with matter, so then everything is in equipartition. And then if you use the expression which we had for luminosity before, you again has a kind of expression finally in Gauss, which shows you the scale. With radius, of course, if you have large body, you have lower magnetic field, Eddington ratio, but also the scaling with mass. And notice that here the scaling is as a square root of mass. Many things scale linearly with mass, but magnetic field scales as a square root. It's quite important difference. And then another thing which is very important, it's evolutionary timescale. Evolutionary in the sense how long the accretion has to proceed before the mass of the central source is going to change. And you can express it easily by dividing the mass by the accretion rate, right? It has right units. And then if you use the expression which we had before, so Eddington luminosity and efficiency will have to appear here. You get again something from in Polish. Sorry, you will learn Polish as a result of this lecture. That means years. 10 to 8, 3 times 10 to 8 years, and here is efficiency. So if the efficiency is 10%, this is actually 3 gigayears. It is very, very small, a very long time scale. It is, by the way, called Salpeter time scale. And notice also that it is identical for galactic sources and for AGN. It does not depend on mass. So if we observe AGN or a galactic source, we don't have to worry about the change of the mass. This will never happen in our life, right? On the other hand, this is really a big problem for interpretation of the evolution of massive quasars at large redshifts. So the record holder, I think I'm correct, is still this source discovered years ago, something like that, at redshift 7.54. So this light from this quasar was emitted when the universe was less than 1 gigayear old. But I told you that the doubling of the mass happens in 3 gigayears. So how this stupid thing could grow? Of course, you can try to play with efficiency, putting 1, but still, it's not quite working. So people, of course, worry quite a lot about this. This is a kind of plot taken from presentation by Shavinsky. This is this guy who was doing Galaxy Zoo, if you know the program. He was the main guy behind it. And here you see the redshift. Here you see the black hole mass measurements. Those are actual measurements from surveys. This is the black hole of M87 black hole mass. This is the Milky Way, Sagittarius A star, small thing. But this kind of quasar I mentioned just would be somewhere here, right? And here there are some scenarios how those quasars can develop, but here you would really require to grow it with efficiency much larger than 1. So frequently people evolve quasars from population 3 stars. Stars which have mass like 100, 200, few hundred solar masses, but that's really slow. That's okay for quasars which start to shine at redshift 5, but not earlier. Direct collapse, but then which mass you should start with, it's not quite obvious. And of course, mergers of black holes. This is probably the only solution, because there is no other way to produce those few highly distant quasars. And in addition, those quasars look really pretty normal. I even checked for that one. It even has a detection in X-rays. They detected, I think, 16 photons from this quasar, and the photon, well, the ratio between the optical and X-ray is pretty normal. So it developed like all other quasars. Oh, going in the wrong direction. Okay, there is one more digression which I should warn you. In the case of a black hole, this is not a problem. If you have accretion, then the black hole mass is rising, although it can lose some mass as a result of energy extraction. We'll talk about it later. But in the case of a white dwarf, the evolution is more complicated, because actually, statistically, the white dwarf loses mass as a result of accretion, because it has nova episodes, ejections, due to thermonuclear flashes. And if you remember, we talked about efficiency of thermonuclear processes and the efficiency of accretion in the case of white dwarf. That is not so highly efficient. So thermonuclear flash can actually remove the accreting material during the ejection. So during the nova episode, the white dwarf will lose more energy than accreting between the 2 episodes. So the mass can be really decreasing. Now, the luminosity. Again, something immense, sorry for that. Well, determination of the luminosity is very difficult, because the problem is basically the distance determination, right? A good example, which I describe here in some detail, is the case of gamma ray bursts. Now, of course, we know they are at cosmological distances, no problem. But when they were discovered, there was a lot of discussions. Some people postulated that the signal comes from the solar system when comets hit something or collide with themselves or something like that. Because we saw just gamma ray flash, shorts lasting a fraction of a second or several minutes. And that was basically it. Then statistics was built, and it looked like the space is not filled uniformly with those bursts. So the number of weaker bursts was smaller than expected from an infinite sphere. And in that case, there were two possibilities discussed. Either they come from the halo of the Milky Way, which also finishes, or from cosmological distance, where finally we are short of sources because of the evolution of the universe. And the key observation was by the telescope PAS, which had both the gamma ray and X-ray camera. It was a small telescope, but it has those two cameras. So it localized the X-ray source with much higher accuracy than the gamma ray source. And small error box allowed immediately to also recognize the optical counterpart. And with optical counterpart and spectra, we had absorption lines, we had the host galaxy, we had everything, we had redshift. And all the problem was solved. The second problem, not so critical, but still quite a pain, is when we want to determine the bolometric luminosity. We need the full coverage of the spectrum. And now with many satellites, we are doing not that badly, because, well, in the case of ground observations, we talked about that. We have we can observe in radio, but in the optical, but we cannot observe directly in gamma ray or in X-rays or in infrared. But we have satellites, so this is not a problem. However, in the far UV, this is really hopeless, because then we have the extinction in our galaxy. This is the cross-section for extinction. This is the wavelength. So this is the optical part. This is X-rays, and this is the peak in near UV when the hydrogen becomes ionized. So here hydrogen is so the absorption on hydrogen is just everything. There is also dust scattering here. So all this happens in the interstellar medium, and we cannot avoid this extinction problem because we cannot send a satellite outside from the Milky Way, right? We cannot reach the nearest planet. So this is a real problem, but we have to live with that. Next, radius. Here the situation is somewhat improving, although in many cases this is still impossible to measure the radius directly, the size of the object, right? In X-rays, for example, this is the Chandra image of a jet. This jet is well resolved in X-rays, but this is because the jet is really enormous. The size of the jet is 300 kiloparsec. So it was possible to measure. A much higher accuracy is in mid-infrared. And then you can map the emission in a number of galaxies. For example, this is the Seepert galaxy in GC 1068. Of course, you do not see the black hole here or the broadline region or anything like that. but some molecular clouds, narrow line region can be resolved. VLBI is doing, of course, nicely. This is water maser observation. So in standard optical observations, we have the angular resolution of 1 arc second. And this, for the galactic sources, this kind of resolution, it corresponds to 10 to 11 Schwarzschild radii. So this is really not fantastic. Even pushing this resolution will not help. For Milky Way, this is 10 to 6. So this is why going down by 6 orders of magnitude, we are there, right? With Event Horizon Telescope. For massive black holes, usually it's not so fantastic because this factor is 10 to 9. But it's interesting to note that whether we observe nearby AGN or distant AGN, this spatial resolution is more or less the same, because usually black hole mass is larger at more distant AGNs. So the characteristic mass of a distant quasar is 10 to 9, while for Seyfert galaxies is 10 to 7. So those two things compensate. For M87, this is 10 to 6. Well, I didn't calculate precise values. It's the same as for Sagittarius A star, for the reason I mentioned. So I already mentioned you the case of M87. We are really doing very, very nicely resolving this black hole shadow or silhouette. We can discuss that. But there was also recently a very nice progress in observations in the near infrared. There is new instrument named Gravity working on VLT telescopes. And this instrument, for the first time, was able to resolve the broadline region in the quasar 3C273, this most famous quasar. Of course, they did not observe in the optical band the near infrared, and this is interferometry, so they did not observe optical lines, but Paschen alpha from hydrogen. But nevertheless, they were able to notice that the emission comes from a rotating disk, which is kind of geometrically thickish. So this is this kind of picture of the broadline region, which is now, this is the first broadline region ever resolved. So in most cases, we cannot resolve things directly, so we have to use some kind of tricks. For example, for binary systems, we use eclipses quite traditionally. Or if we know the luminosity and the temperature, we can calculate the radius, but then we rely on theory. Also, we can use variability. But there are also very special methods. I would like to mention that one because it is gaining importance now in cosmological applications, although the method is known since, I don't know, since 80s. This is the gravitational lensing. The setup is the following. We have the quasar, which is behind the galaxy, just one quasar behind the galaxy. But because this galaxy, which is at intermediate redshift between quasars and us, is bending the light, leading to creation of 4 images. And so then you see a quasar as 4 separate images, 4 quasars. Those images vary. You can see that this is from the paper of Michał Jaroszyński from the Warsaw Observatory, who did it in 94. He didn't do the observation, but he did the interpretation. So you see, here is image from 81, here is image from 84. So you see, it's the same, it's just the core. So now this image is brighter, this is not so bright. Now those two are comparable. So this is because of the quasar intrinsic variability. On the other hand, each of those images is doing continuous flickering. And this continuous flickering is due to the fact that in this galaxy we have individual stars, and all passing star is bending the light. So then you have to create a map of the amplification, and this kind of amplification map moves across the field of the quasar. So in the old paper of Michał Jaroszczyński, he was only able to report the upper limit for the optical size of the quasar behind, and it was a few times 10 to 15 centimeters. But more recent results from 2015 gives already more accurate results with both upper and lower limits. So the optical size of these quasars is 2 times 10 to 15 centimeters plus minus 1. And that corresponds to 5 Schwarzschild radii. We really see the emission which originates close to ISCO. Now, mass determination. Mass determination in astronomy since, I don't know, Copernicus or whatever, right? Earlier, old Greek times, is done using Keplerian motion. So if you have a central body and if you have a satellite, you have to measure the radius, and you have to measure the velocity or the period, and then you can calculate the mass from this simple prescription. The problem only is to find the proper satellite, right? In the case of a binary stars, if one star, for example, the donor star is well seen in the optical band, then you can measure the velocity from line shifts, and you can measure the period, and you have the mass. Of course, the inclination angle is a problem, but in the case of AGN, for example, in the case of Sagittarius A star, you can use the motion of individual stars. There are a number of stars which were followed close to the nucleus, and this is how the black hole mass was measured quite precisely. On the other hand, you in other more distant AGNs, you can use, for example, gaseous clouds, and this is this so-called broadline region. We will talk more about the broadline region on the next lecture. But here I just show you the very old plot from 1999. Because it is a collection of really large number of measurements in a single source. What those people, Van der et al., measured was to measure the line width for several lines, like carbon 3, helium 2, carbon 4, of course, H beta somewhere should be somewhere here. Yes. A lot of lines. Then they measured the time delay with which the lines respond to the change of the continuum. And that light travel time gave them the radius. So for each of those measurements, they had radius from time delay and velocity from the line shape. So they were able to calculate the black hole mass from each of those individual measurements. And they were really very happy that they got more or less the same result from all those measurements, right? If the methodology would be wrong, it would be completely random, like 1 point here, 1 point here. They got the result in 8 times 10 to 7, more or less, in solar units. We will talk more about that when we will later talk about Geoplanet region in more detail. Now, it's nice to know that those parameters are useful, but we should measure them, right? I already mentioned some problems in measurements, but now we'll talk about some interesting examples of how to measure things in a very unexpected way. Not really obvious, but very intelligent. So accretion efficiency. And the method was invented not years ago, although it's kind of obvious if you think about it, but it was really invented and published by Andy Fabian in 1979. What is the setup? How to calculate accretion efficiency in an easy way? First, you do a lot of assumptions and you do a lot of formula, and then it will come. But first, you have to assume that you have a source of radiation. Let's say this is this kind of cloud which emits photons. The average luminosity is L, but it changes significantly. Let's assume that we measure this significant change which happened in certain time scale. Like, let's say, luminosity changed by a factor of 2 in 1 day. And he showed that it's possible to use that immediately to calculate the accretion efficiency. So let's assume that the photon is traveling across this kind of cloud. The radius of the cloud, we don't know it, but we will mark this radius as r, and the optical depth of the cloud we will mark as tau. Later, it will be the key point to get rid of those values, but we have to go step by step through this kind of reasoning. So we can have, in general, two situations, and we don't know, in principle, which situation we deal. First, the medium can be optically thin, right? So in that case, the optical depth is much lower than 1. If the photon is emitted somewhere, it will just cross the region and escape. So as for order of magnitude, the travel time across the region would be just the size of the region divided by light speed, as for the order of magnitude. It's more complicated if the medium is optically thick. Then the photon is going several times here, just getting scattered. So we have to include now a lot more parameters, and we will later try to get rid of those parameters. So we assume that there is a mean free path for the photon, and then if we have n scatterings, then traveled distance by the photon is n times the mean free path. But we know from the Brownian motion that, of course, the photon is not scattered in preferred direction all the time, the same direction. So in the Brownian motion, the systematic shift is the mean free path but times the square root of the number of scatterings. So the drift is much slower. So now the mean velocity, mean drift velocity is the shift divided by this covered path divided by the velocity. So as a result, the mean drift velocity is the light speed divided by the square root of n. So if the number of scatterings required is large, then of course the drift velocity is pretty slow. So now we consider the photon which finally left the cloud. So then the shift of the photon is equal to the radius. The optical depth, on the other hand, is equal to the number of scatterings. So from that, we get that the crossing time is actually, again, the ratio of the size to the divided by the light speed, but now it is multiplied by tau. And sometimes I use this, sometimes that, because if I do the formula in LaTeX externally, then I have tau, and here sometimes I'm too lazy to put this, many whatever Greek alphabet, and sorry for that, but I think it's not really misleading. So combining, so now we have this kind of expression and this kind of expression. So it's not good to have two expressions because we don't know in advance whether this medium is optically thick or optically thin. So what we do here, and this is what we do very frequently in astronomy, we have two limits, then we sort of invent bridging formula, which in that case looks like this, right? It looks good because if tau is small, then it reduces to this one. If tau is large, then 1 does not matter. Who cares about 1 if tau is 10? So this is really excellent universal formula for all cases, whatever the optical depth is. Here we have to relate now, we have to do something with the optical depth. So we are working now through the structure of the cloud. First, we relate the optical depth to the Thomson cross-section, cloud cloud density. Here, this is in grams per cubic centimeter, and this is why the proton mass appeared, and this is the size of the cloud. So we can determine the density of the cloud from this formula, and we can determine the mass of the cloud. Now we express the radius of the photon, and we start with the expression of for the efficiency. So this is the luminosity times this crossing time divided by mc squared, and we put what we had before. So tau plus 1 appeared in this here. I hope I did not make a mistake in this derivation, although I'm not quite sure. Perhaps you can check it later, because if I now start to checking, then we will spend quite some time. Here we have tau. We have tau plus 1. I worry about here there should be a large R, not small r, and this is where R also appeared. So you have to go through this formula quite carefully. So this R will go here. So it's a bit more of work than it's just written on those slides, but it's not conceptually difficult, I suppose. So what you get is finally this kind of result, where T is this variability time scale which you measured, and this is the time scale which we used for photons to leave the area. This is the luminosity. This was measured. But now we have this kind of stupid expression which depends on tau. And we don't know tau in advance. And this is the intelligent thing which was noticed by Andy Fabian. This function is not monotonic. This has a minimum. Because if tau is large, it's large. If tau is very small, it's also large. So it's a kind of semi-parabolic with a clear minimum. So if you take the minimum of this value, and the minimum value is equal 4, I guess, then you can get that the efficiency is higher always than what you can measure. So it's not quite the measurement of efficiency, but assuming that we are not too far from the minimum, this will do. I'm not sure if you are convinced. Not quite. I think it's really necessary to derive it for yourself and see how it's really working step by step. It's a good exercise because, well, this kind of bridging formula and this kind of minimum, this is frequently used because, you know, it's always good to have numerical results, but sometimes analytical results are much faster. And then you get analytical results usually in certain limits. Then you take one limit, other limit, and then you have bridging formula. And then you do this kind of play. It's a very frequent methodology. So, question?
No, it's okay.
Yeah. So, for example, if we take the case of NGC 5548, we will talk about this source later on because the observational data for this AGN is really quite fantastic recently. But let's assume that the X-ray luminosity of this source is of order of 10 to 44 ergs per second. And it significantly changes in 10 to 4 seconds, which is true. In X-rays, it varies quite fast. Then I think you can get the efficiency from this formula 0.02. That's not a very high efficiency, but that's not surprising. The inner flow in this AGN is kind of optically finite. So it's less efficient than standard accretion disk, 10%, which I'm using. On the other hand, there are AGNs for which if you use this formula, then the result is that efficiency is much, much larger than 1. And this is not just a stupid result. This means that some underlying assumptions are incorrect. And in this case, this is beaming. If you take relativistic beaming, then of course, this kind of thing is not included because time scales are different, everything. So this kind of method was sometimes used to select BLux or blazars in general, because you do variability, and all those which have efficiency much larger than 1, they are blazars. As simple as that. Easy to check if you have a catalog of hundreds of thousands of sources with some information on variability. Very practical. Now, the second example of the intelligent method to calculate the efficiency. It's also used from time to time, and it's quite important and quite strong if you want to determine the spin evolution across the ages or whatever. Because the direct spin measurements in AGN is quite difficult and unreliable. And the idea was invented, as you can see, 1982, so quite some time ago. It was basically suggested by Bogdan Paczynski, but really done by Andrzej Sultan, and in the English literature, it is known as Sultan argument, and it was very difficult to translate it really into Polish, because argument Sultana does not sound that great, but there is no other equally good translation into Polish. So the fact that it has nice name means it's important and used quite a lot. How it works? That's not that simple. So that is the method to calculate the mean quasar efficiency. So in order to calculate efficiency, you would first start with calculating the mass, which accumulates at the center of a quasar of a luminosity L during its lifetime T. So then if you know this efficiency, then you calculate the mass, but of course we will try to invert the argument later on to get the efficiency. So in principle, this is a simple expression. The luminosity can change with time. Why not? It should actually change with time. And the problem is that you don't know that the active time of the quasar. You do not know how this luminosity of this stupid quasar changed during its lifetime. So instead of concentrating on a single quasar, we go to statistics, to many quasars. And we try to calculate the amount of energy which accumulates or was produced in 1 gigaparsec, cubic gigaparsec. For that, we would do the integration. Now it looks like double integration, looks even more hopeless. And for that, we need the number of quasars of a given luminosity at any given moment of time. So, and we have to integrate that over the luminosity and again over time. But at least in now integration over time is seems quite much simpler, because we should integrate from the Big Bang or from the first quasars like redshift 7 to now. The problem is that we don't know this part. But now, this is the key point of the method. We assume that cosmological model like Friedman model is on average uniform. So whatever happens here happens also at larger distance. Statistically, it's the same. Because our location in the universe is not a special location. On the other hand, in observations, if you think about time, then in reality you think about redshift, right? Because astronomy is both like geography and history. You go to distance objects, they are younger, so there is this element of time, but there is redshift. So instead of this quasar, which we were interested in many years ago, which we have no idea how Milky Way looked a billion of years ago, we are using another galaxy, which is similar, but now it's at a redshift, which is corresponding to 1 giga-year ago. So instead of integrating over time, which we cannot do, we have no idea how to do it. We are integrated over redshifts, and we are integrated known quasars over redshifts. And that is doable, right? We have the statistics of redshifts at a given redshift. We know how many quasars we have at a given luminosity, or actually we go from luminosity to the observed flux because that's easier. So this is really a very important trick. Of course, it requires this kind of assumption that what we see now at large radius is what happened here years or billions of years ago. So we integrate the energy in this way by integrating really observed quasars. And then we measure the black hole mass which accumulated nearby. And we divide one thing by the other, and then we can calculate the efficiency of accretion in such way. Because we have two numbers, we are able to estimate. So that came from the integration, and then this was compared to the number of black holes which were measured locally. And in his original paper, Andrzej, I think, is quite careful. He just said that this efficiency is higher or the order of 10%. Later on, this method was used several times. I didn't look for the most recent application, but the older one is quite interesting. For example, Davis and Laur are getting strong dependence on this efficiency on black holes. They separated different black holes. They didn't do an integration of everything. They separated masses, and they got that the efficiency is rising from 0.03 for smaller masses to 0.4 for large masses. That suggests a kind of evolution of the spin. So lower mass sources have lower spin and higher mass sources have higher spin. That was the conclusion of this paper. Of course, those computations are not very simple, but nevertheless, this 10% efficiency on average with some trend over the redshift, rather higher efficiency in the past and rather lower efficiency now, it repeats in all computations. And that also suggests that actually most of the black hole growth happens through the bright quasar stage, right? Because if most happens through mergers, this efficiency would be lower. So we need multiple mergers to create the early quasars, most massive, highest redshift quasars. On the other hand, to create everything else, all those quasars which pile at the redshift 2, we don't need anything very special. It's just more or less Eddington accretion rate of bright quasars, and then there are remnants nearby. Yeah, accretion rate. Well, that is difficult. In the case of binary systems, sometimes we can estimate the accretion rate that from the models of the binary evolution. On the other hand, because the accretion is not really stationary, this is highly uncertain. So usually we do not measure the accretion rate directly from observations. And we are quite close to the end. Temperature and maximum energy of photons. Well, that's easy, right? If you have a spectrum and, for example, you have something which looks like a black body, you can measure the temperature. If it's something which does not look like a black body, but still it has a kind of a band at 100 keV, whatever, that means it's optically thin medium, but still electrons which are shining are more or less thermal. So from this position, from this band, you can measure the temperature of order of 100 keV. So measurement of the temperature is simple. Global evolution, we cannot say anything about global evolution because we have no patience and no grants covering 10 to the 8 years, right? So only from evolutionary stages and statistics we can have some idea about this. On the other hand, short-term variability, we will talk a lot about it because it is really a key to understand many phenomena in the sources. And now bad news, there is a homework to do.
It's in Polish.
Oh, that's in Polish.
It works for you.
Yes. No, I will translate that for you.
So my homework can be to translate, okay?
No, that would be too simple. Okay. The first 2 points are sort of obligatory. The third one, if you are interested, because this is more difficult. So first one is in English. Calculate your personal Eddington ratio and report it. Second, calculate the Eddington limit for the atmosphere which is dominated by electron-positron pairs. Not just ionized hydrogen. It will be different. So calculate it. That's easy, but you have to think what to change. And the third one was to show how we do in this Sultan argument, how we do this transition from the time integration to redshift integration. So you can try to look into the original paper of Andrzej, or if you don't understand, go and ask the author, right? So that's it for today. Thank you.